In this section, we're going to talk about electric current and resistance. So imagine we have a circuit, kind of like the capacitor circuit I showed you earlier. I'm going to draw it for you. Now, there are a lot of new symbols here. We've already talked about this, which represents a voltage. Often we make that a V. But we haven't talked about this symbol, right here. Jagged lines up and down. And this is a resistor. And we call that R. And we also have another constant, and that is I. I, we call, is current. So we have these three things: voltage, current, and resistance. But what are these things? Voltage, we've talked about in previous lectures. Imagine voltage is height, or power, or the ability to do something. That's what voltage is. It has units of volts. It's what pushes the circuit. And then we have resistance. And resistance resists that push. But what's being pushed? What's being pushed is electrons. Electrons are being pushed by this voltage because they have charge. Resistance is resisting that push. And the speed of those electrons, or how many are moving for a certain amount of time, that is current. So think voltage the push, current's the speed, resistance is what's holding back. Now, I'm going to introduce a new, very important equation, and that is Ohm's law. And Ohm's law is this: voltage equals current times resistance. Voltage, or the push, has units of volts. Current has units of amps, which that's new, and amps are coulombs per second. So it's charge per second. So think of it as how many electrons are moving per second. And resistance has units of ohms. We call this ohms. It's a funny looking symbol. Now, different materials have different properties, and one of those properties is resistance. So, we've talked about conductors, like metal, and conductors have low resistance, and that's because charge can easily flow, or current. So if current can easily flow, then it has low resistance. Another thing is, if we have a wire, and this has the face has area A of length L. If we increase the length, we increase the resistance because it has to travel over a greater area. If we increase the area, then resistance decreases because it has a larger surface to go through. Which introduces us to a second equation. Resistance equals resistivity times length over area. Area is the surface area of the face. Length is the distance you travel. And resistivity is a material property. So iron will have a certain resistivity, copper will have a certain resistivity, and all materials will have a certain resistivity. And if we know the length that current travels through that material, and we know the area that it travels through, we can calculate the resistance of the system. The reciprocal of resistivity is conductivity. And that is equal to 1 over resistivity. Now, if we change the temperature of the system, the resistivity is going to change. So if we heat up copper, the resistivity of copper is going to increase. And that leads us to this equation. Resistivity due to temperature is equal to resistivity initially at a certain temperature, 1 plus alpha, alpha is a constant, times T minus T naught. T is not time, it's temperature. The resistivity of the material at temperature T naught is resistivity naught. Alpha will be given in the question. Temperature, this T represents the final temperature of the system, and resistivity T represents the final resistivity of the system. Now, there's another equation that links to Ohm's law right here. The voltage equals current times resistance, which we use to solve for a certain constant in a circuit like this. And that is power. Power, we know, is the ability to do work over time, or to exert energy over time. So we know that has joules per second. Another unit for joules per second is just calling it watt. Joules per second is the same thing as W, or watt. Now, power for this electrical system is equal to the voltage over the current. So it's voltage times current. And this makes sense because power is like a force applied over a distance in a certain amount of time, because it's energy per second. So it's like the push times how far it's pushed in a certain amount of time. Using Ohm's law, we can transform the power equation, and we can transform it to V squared over R, voltage squared divided by resistance, and we can also transform it into I squared, current squared, times resistance. So taking this right here, plugging in different values for Ohm's law, changing the power equation to other things. Now, we often talk about energy. When you're looking at your electric bill, you use a certain amount of energy. And that's power applied over time, so it's joules. So I'm going to give you a certain unit that may be tested, and that is kilowatt hour. And a kilowatt hour is equal to 3.6 times 10 to the 6th joules. So you're going to memorize this because you may have it on the test, and they may have you convert to kilowatt hours. A final circuit element we're going to talk about is a fuse. And we have fuse drawn like this. So for a fuse, if a certain amount of current passes through the fuse breaks. You will have these in your houses, in your homes, and it protects your house from electrical fires because it keeps current from getting too high. Now, we talked about current, and we said that current is coulombs per second, or amps. A is amps, amperes. So that's change in charge over time. Now, charge we think of is, electrons or protons. And that's the movement of how fast they go, or not how fast they go, but the change in charge in a system in a certain amount of time. So, current is not the movement of electrons, though. Current is the movement of positive charges. It's a funny thing they did when we invented all this physics stuff. It should be the other way, but in physics, current moves in the opposite direction of electron flow. Current is the flow of positive charges.